When I was a kid, we knew about 9 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto, back when it still counted. 9 worlds orbiting our sun. And that was it. That was the entire list of known planets in the universe. We assumed other stars probably had planets too, but we had no proof, no evidence, no way to find them. We were looking out at a cosmos filled with hundreds of billions of stars in our galaxy alone, and we couldn't answer one of the most basic questions you could ask. Do other stars have planets like ours? Are there other Earths out there, other Jupiters, other worlds where rain might fall or winds might blow or oceans might crash against alien shores? We didn't know. We could only guess and hope and imagine. Today, everything has changed. We're not guessing anymore. We're not wondering if other stars have planets. We know they do. We've found them, we've detected them, we've catalogued them, and the number is staggering. As I'm speaking to you right now, we've confirmed the existence of more than 5,000 exoplanets. 5,000 worlds orbiting other stars. 5,000 planets beyond our solar system that we've actually detected and verified. And that's just the confirmed ones. There are thousands more candidates waiting for verification, and beyond those candidates, statistical analysis tells us that essentially every star in the galaxy has planets. Billions and billions of worlds that we haven't detected yet, but that must be there based on everything we've learned. We've gone from knowing 9 planets to knowing that planets are everywhere. That they're the norm, not the exception. That the universe is full of worlds beyond counting. This transformation happened in my lifetime. In your lifetime, if you're old enough. This is not ancient history. This is not something our grandparents discovered. This is happening now. This is a revolution in human understanding that's unfolding in real time. And most people have no idea how profound this change really is. Tonight, I want to take you on a journey through this revolution. I want to help you understand not just how many exoplanets we've found, but what that number means, how we found them, what kinds of worlds they are, which ones might harbor life, and why this discovery changes everything about how we see ourselves and our place in the cosmos. Because when you really grasp what we've learned about exoplanets in the last 30 years, when you understand the sheer number and diversity of worlds out there, it shifts something fundamental in your perspective. It makes Earth feel less lonely, but also more precious. It makes the universe feel more full, but also more mysterious. It raises new questions, even as it answers old ones. So, let's start at the beginning. Let's go back to a time before we knew about any exoplanets. Let's understand what changed and why it matters so much. For most of human history, we didn't even know that planets were worlds. The ancient Greeks saw them as wandering stars, lights in the sky that moved differently than the fixed background stars. They didn't know planets were physical places. They didn't know Earth was a planet. They didn't understand the solar system at all. It took thousands of years to figure out that Earth and the other planets orbit the Sun. That took Copernicus and Galileo and Newton. It took careful observation and mathematical reasoning and the courage to challenge old assumptions. By the early modern era, we understood our solar system reasonably well. We knew the planets, their orbits, their basic properties. We'd discovered Uranus and Neptune through telescopic observations. We understood that these were worlds, physical objects with surfaces and atmospheres and moons. But we only knew our solar system. We had no idea if other stars had planets. It seemed reasonable to assume they did. After all, if our sun has planets, why wouldn't other stars? But assuming something and proving it are very different. We needed evidence. We needed a way to detect planets around other stars. And that turned out to be incredibly difficult. Here's why. Stars are bright, incredibly bright. Planets are dim. They don't produce their own light. They only reflect starlight. And the amount of light a planet reflects is tiny compared to the light from its star. Jupiter, the largest planet in our solar system, reflects about 1/1000th of the Sun's light. 1/1000th. Trying to see Jupiter next to the Sun from another star system would be like trying to see a firefly next to a searchlight from across the country. The firefly is there, but the searchlight drowns it out completely. You can't see it no matter how good your eyes are, and planets are also small compared to stars. The Sun is more than 10 times wider than Jupiter, the biggest planet in our solar system. Earth is more than 100 times smaller than the Sun in diameter. From another star system, Earth would be a tiny dot next to a blazing ball of light, completely invisible. So, for a long time, astronomers thought finding exoplanets would be impossible. Not just difficult, impossible. The technology didn't exist. The techniques didn't exist. We were stuck knowing only our own solar system, unable to answer the question of whether planets were common or rare in the universe. But some astronomers didn't give up. They kept thinking about the problem, kept developing new techniques, kept pushing the boundaries of what was possible. They realized that even if you can't see a planet directly, you might be able to detect its effects, its gravitational influence on its star, the tiny dimming of starlight when a planet passes in front, the slight wobble in a star's motion caused by an orbiting planet. These indirect methods might work. They might allow us to find exoplanets even if we couldn't photograph them directly. And in the early 1990s, one of these indirect methods finally paid off. In 1992, astronomers Alexander Wolszczan and Dale Frail announced the discovery of 2 planets orbiting a pulsar. A pulsar is a rapidly spinning neutron star, the collapsed core of a massive star that exploded as a supernova. Pulsars emit regular pulses of radio waves as they spin like a cosmic lighthouse. These pulses are incredibly regular, so regular that they can be used as precise clocks. Wolszczan and Frail were studying a pulsar called PSR B257+12, monitoring its pulses. And they noticed something strange. The pulses weren't perfectly regular. There were tiny variations in the timing. The pulsar was wobbling slightly, and the pattern of the wobble suggested that planets were orbiting the pulsar. The gravitational pull of the planets was causing the pulsar to move in a small circle, and this motion affected the timing of the pulses we detected. By analyzing the wobble, they calculated that there were at least 2 planets, and later a third was confirmed. These were the first exoplanets ever discovered, but they were strange ones. Planets orbiting a pulsar, a dead star. The intense radiation from the pulsar would make these worlds utterly hostile to life. They were fascinating from a scientific perspective, but not the Earth-like worlds we hoped to find. Still, it proved something crucial. It proved that planets exist around other stars, that our solar system is not unique, that planet formation can happen in different environments. The discovery opened the door. It showed that finding exoplanets was possible, and it motivated astronomers to keep searching. Then came 1995, the year everything changed. On October 6, 1995, two Swiss astronomers, Michel Mayor and Didier Queloz, announced the discovery of a planet orbiting 51 Pegasi, a sun-like star about 50 light-years from Earth. This was the first confirmed exoplanet orbiting a normal star. Not a pulsar, not a dead star. A regular, main-sequence star like our Sun. This was a game-changer. They used a technique called the radial velocity method, also known as the wobble method. Here's how it works. When a planet orbits a star, it doesn't just orbit while the star stays still. Both the planet and the star orbit their common center of mass. For a star with planets, this center of mass is close to the star's center, but not exactly at it. So as the planet orbits, the star wobbles slightly. It moves in a small circle or ellipse. This motion causes the star's light to be Doppler shifted. When the star moves toward us, its light is blue shifted to slightly shorter wavelengths. When it moves away, its light is red shifted to slightly longer wavelengths. By measuring these tiny shifts in the star's spectrum, astronomers can detect the wobble, and from the wobble, they can infer the presence of a planet. They can calculate the planet's mass, its orbital period, and its distance from the star. Mayer and Queloz detected a planet orbiting 51 Pegasi with a period of just 4 days. 4 days. That means this planet completes a full orbit around its star in less than a week. Our Mercury, the closest planet to the Sun, takes 88 days to orbit. This planet was orbiting much closer and much faster, and when they calculated its mass, they found it was about half the mass of Jupiter, a gas giant, orbiting incredibly close to its star. This was shocking. At the time, our understanding of planet formation suggested that gas giants should form far from their stars, where it's cold. That's where Jupiter and Saturn are in our solar system. We didn't think gas giants could exist close to their stars. The heat would prevent them from forming. But here was one. A hot Jupiter, as they came to be called, a gas giant orbiting so close to its star that it was roasted to temperatures over 1,000 degrees Celsius. Its atmosphere was probably being blasted away by stellar radiation. It was nothing like anything in our solar system. This discovery did two things. First, it proved that planets orbit other sun-like stars. We now had solid evidence that planetary systems are not unique to our Sun. Second, it showed us that planetary systems can be very different from ours. That the solar system we grew up learning about is not the template for all planetary systems. That nature can create worlds and configurations we never imagined. The discovery was controversial at first. Some astronomers questioned whether the signal was really from a planet or from something else. But within months, other teams confirmed the finding. And then, more exoplanets started being discovered. In 1996, several more were announced. In 1997, even more. The floodgates had opened. Astronomers had figured out how to detect exoplanets, and they weren't rare. They were everywhere. The radial velocity method was finding them left and right. And then other methods started working too. In 1999, the first exoplanet transit was detected. A transit is when a planet passes in front of its star from our perspective, blocking a tiny fraction of the star's light. If you measure the star's brightness precisely, you can see it dim slightly during the transit. The amount of dimming tells you the planet's size. The timing tells you its orbital period. This transit method opened up new possibilities because it could detect smaller planets that the radial velocity method might miss, and it could be applied to thousands of stars simultaneously. You could monitor many stars at once, looking for the telltale dips in brightness that indicate transits. Over the next decade, the number of known exoplanets grew steadily. By 2000, we'd found about 50. By 2005, about 150. By 2010, about 500. The numbers were climbing, but we were still in the hundreds. Then the Kepler Space Telescope launched in 2009. Kepler was designed specifically to find exoplanets using the transit method. It stared at a single patch of sky containing about 150,000 stars and monitored their brightness continuously for years. The data it collected revolutionized the field. Kepler found thousands of exoplanet candidates. Thousands. In its 9 years of operation, it detected over 2,700 confirmed exoplanets and thousands more candidates. It showed us that planets are incredibly common, that most stars have planets, that Earth-sized planets exist, that multi-planet systems are normal. The Kepler mission transformed exoplanet science from a niche field to a major area of astronomy, and other missions joined in. The TESS mission, launched in 2018, is scanning nearly the entire sky for transiting exoplanets. Ground-based surveys using the radial velocity method continue to find planets. Other space telescopes contribute discoveries. The count keeps rising. Today, as I said at the beginning, we've confirmed over 5,000 exoplanets, and there are thousands more candidates awaiting confirmation. The number grows almost every week. New planets are being announced regularly. We're living through the golden age of exoplanet discovery. Now, let me explain the detection methods in more detail, because understanding how we find these planets helps you appreciate how incredible this achievement is. Let's start with the transit method, since it's responsible for most of our discoveries. Imagine you're looking at a star. It has a certain brightness. Now imagine a planet orbits that star, and from our viewing angle, the planet passes directly in front of the star during part of its orbit. When this happens, the planet blocks some of the star's light. Not much. For a planet the size of Jupiter blocking a sun-like star, the dimming is about 1%. For a planet the size of Earth, the dimming is about 0.01%. 1/100th of 1%. This is a tiny change. You can't see it with your eyes. You need precise instruments that can measure a star's brightness to better than 1 part in 10,000. But we have such instruments now. Space telescopes like Kepler and TESS can measure brightness to extraordinary precision, and when they detect a star that dims regularly by a small amount, that's a candidate exoplanet. But you can't confirm it from one transit. You need to see it happen multiple times. If it happens again with the same period, the same amount of dimming, the same duration, then you have strong evidence of a planet. The period between transits tells you how long the planet takes to orbit. The amount of dimming tells you the planet's size relative to the star. If you know the star's size, you can calculate the planet's actual size. The duration of the transit tells you about the orbit's geometry. All of this from a tiny dip in the star's brightness. It's remarkable. But the transit method has limitations. It only works if the planet's orbit is aligned just right from our perspective. If the orbit is tilted so the planet doesn't pass in front of the star from our viewpoint, we won't see transits. Statistically, for randomly oriented orbits, only a small fraction will transit from our perspective. Maybe 1% for close-in planets, less for distant planets. So even though Kepler stared at 150,000 stars, it could only detect transits for a small fraction of the planets that might be there. Also, the transit method gives you the planet's size, but not its mass. To get mass, you need a different method. That's where radial velocity comes in. The radial velocity method, the wobble method, measures the star's motion. As I explained, when a planet orbits a star, the star wobbles. This wobble causes Doppler shifts in the star's spectrum. By measuring these shifts, you can detect the wobble and infer the planet's presence. The radial velocity method gives you the planet's mass, or at least a minimum mass if you don't know the orbit's inclination. It also tells you the orbital period and the distance from the star. But it's harder to detect small planets this way. The wobble is proportional to the planet's mass and inversely proportional to its distance from the star. So massive planets close to their star cause bigger wobbles and are easier to detect. Small planets far from their star cause tiny wobbles that are hard to measure. This is why the first exoplanets discovered were hot Jupiters. They're big and close, causing large wobbles. Earth-sized planets far from their stars are much harder to detect with this method. We're getting better at it, but it's still challenging. When you combine transit and radial velocity observations, you get both the planet's size and its mass. From those, you can calculate the planet's density, and density tells you what the planet is made of. Is it rocky like Earth, gaseous like Jupiter, made of water ice? The density gives you clues about composition. This combination of methods is powerful. You get a complete picture of the planet's properties. Then there's direct imaging. This is what most people think of when they imagine detecting an exoplanet, taking a picture of it. But, as I explained, this is incredibly difficult because planets are so dim compared to their stars. It's like photographing a firefly next to a searchlight. To do direct imaging, you need several things. First, you need a really big telescope to collect enough light. Second, you need adaptive optics to correct for atmospheric blurring if you're observing from the ground. Third, you need a coronagraph, a device that blocks the star's light so you can see the faint planet nearby. Even with all this, you can only image planets in specific circumstances. Usually, young planets that are still hot from their formation and glowing in infrared, or massive planets far from their star where the contrast is better. So far, we've only directly imaged a few dozen exoplanets, and they're mostly unusual cases. But direct imaging gives you something the other methods don't: a spectrum of the planet's light. You're actually collecting photons from the planet itself, not just inferring its presence from its effects on the star. This means you can analyze the planet's atmosphere, look for chemical signatures, potentially even detect signs of life. Direct imaging is the future of exoplanet science, but it's still in its early stages. There's also gravitational microlensing. This is a really clever technique based on Einstein's general relativity. When a massive object passes between us and a distant star, the gravity of the foreground object bends the light from the background star. This can cause the background star to appear brighter temporarily as its light is focused toward us. If the foreground object has a planet, the planet's gravity causes an additional blip in the brightness curve. By analyzing this blip, you can detect the planet. Microlensing can find planets at large distances from their stars, farther out than the other methods can detect. It can even find rogue planets, planets that don't orbit any star at all. But each microlensing event only happens once. You can't repeat the observation. You get one chance to detect the planet, and then the alignment changes and it's gone. So microlensing is great for statistical studies, understanding how common different types of planets are, but it's not great for detailed follow-up. Each of these methods has strengths and weaknesses. Each is sensitive to different types of planets. Transit method finds small planets close to their stars. Radial velocity finds massive planets regardless of size. Direct imaging finds young or massive planets far from their stars. Microlensing finds planets at intermediate and large distances, including free-floating planets. By using all these methods together, we're building a comprehensive picture of the exoplanet population. We're finding planets of all sizes, all distances, around all types of stars. And what we're learning is astonishing. Planets are everywhere. They're more common than we imagined, and they're more diverse than we ever expected. So let's talk numbers. As of right now, the confirmed count is over 5,000 exoplanets. This number comes from combining discoveries from all the different methods and missions. Kepler contributed the most, about 2,700 confirmed planets. TESS is adding more every week. Ground-based radial velocity surveys have found hundreds. Direct imaging and microlensing contribute dozens to hundreds. The exact count depends on what you include. Some planets are confirmed with high confidence. Others are still candidates awaiting additional observations. The official catalogs, like the NASA Exoplanet Archive, keep track of the confirmed planets. As of today, the count stands at over 5,000. But this is just the tip of the iceberg. Statistical analysis of the Kepler data suggests that there are billions of planets in our galaxy alone. Billions! The Milky Way has about 200 billion stars. If even a fraction of those have planets, we're talking about hundreds of billions of worlds. And observations suggest that planets are the norm. Most stars have at least one planet. Many have multiple planets. So the real number is probably closer to 1 trillion planets in our galaxy. 1 trillion worlds. And our galaxy is just one of hundreds of billions of galaxies in the observable universe. The total number of planets in the universe is beyond comprehension. But we're not trying to find them all. We're trying to understand the population. What kinds of planets are common? What kinds are rare? Which ones might support life? And the 5,000 we've confirmed so far are enough to start answering these questions. They're a representative sample that tells us about the broader population. Every planet we find adds to our understanding. Every new discovery refines our statistical models. Every detection brings us closer to answering the big questions. Are we alone? How common is life? How many Earths are out there? These numbers, 5,000 confirmed, thousands more candidates, billions estimated in our galaxy, they're not just statistics. They're a revolution in how we see the universe. They represent a fundamental shift in human knowledge. 30 years ago, we knew of 0 exoplanets. Today, we know of thousands. In one generation, we've gone from wondering if planets exist around other stars to knowing that they're everywhere. That's extraordinary. That's a transformation in understanding that happens only rarely in human history. And it happened in our lifetime. We're witnesses to this revolution. We're living through it. And most people don't even realize how profound it is. That's what I want to help you understand tonight. Not just the number, but what it means, how we got here, what we've learned, and where we're going next. Because the story of exoplanet discovery is not just about astronomy. It's about human curiosity, about pushing boundaries, about answering questions that philosophers and dreamers have asked for thousands of years. Are we alone? Are there other Earths, other skies, other sunrises on other worlds? Now we know. There are other worlds, thousands of them, and we're just getting started finding them. The transit method works best for planets close to their stars because those planets transit more frequently. If a planet takes a year to orbit, like Earth, you only get one transit per year. You need to observe for several years to confirm it, but a planet that orbits every few days transits hundreds of times per year. You can confirm it quickly. So, the planets we've found so far are biased toward close-in planets. Hot Jupiters, hot super-Earths, planets with short orbital periods. We're finding these because they're easiest to detect, not because they're necessarily the most common. As our missions run longer and our techniques improve, we're finding planets farther from their stars. Planets with longer orbital periods. Planets more like Earth in terms of temperature and distance from their star. But it takes time. You need patience. You need to keep observing. The Kepler mission observed for 9 years, which allowed it to find planets with orbital periods up to a few years. Future missions will observe even longer, allowing us to find planets at Earth-like distances from Sun-like stars. We're getting there. We're pushing the boundaries of what we can detect, and every year the catalogue grows. Every year we add more planets to the list. The number started at 0, then 1, then 2, then 10, then 100, then 1,000. Now over 5,000. And it's still climbing. This exponential growth shows no signs of slowing. As new missions launch and new techniques are developed, the rate of discovery will likely increase. In 10 years, we might have 10,000 confirmed exoplanets. In 20 years, maybe 50,000. The sky is full of planets, and we're learning to see them. We're developing the tools and the patience to detect worlds that would have been invisible to us just a decade ago. And with each new detection, we refine our understanding. We learn what kinds of planets are common, what kinds of stars host planets, what kinds of orbits are stable, what kinds of atmospheres exist. We're building a science of exoplanets from the ground up, creating theories of planet formation and evolution that match the diversity we're observing. And sometimes we're surprised. Sometimes we find planets that don't fit our theories, that challenge our assumptions, that force us to rethink what we thought we knew. That's the beauty of science. Observations trump theory. Nature is the ultimate judge, and nature has shown us that planets are far more diverse and numerous than we imagined. So, when I tell you we've found over 5,000 exoplanets, I'm not just giving you a number. I'm telling you about a transformation, about a shift from ignorance to knowledge, from speculation to certainty, from wondering if planets exist to knowing that they're everywhere. This is what makes the study of exoplanets so exciting. It's not just about finding new worlds. It's about understanding our place in the universe, about seeing Earth as one planet among trillions, about recognizing that whatever happens on our world is happening on countless others, that the universe is full of places where rain might fall, where lightning might strike, where mountains might rise and oceans might churn. We're not alone in having a planet. We're part of a cosmic norm, and that changes everything. Let me help you understand just how remarkable the detection techniques really are by walking through what it takes to actually find these planets. Because when you grasp the technical challenge, when you see what astronomers had to overcome, it makes the achievement even more impressive. Start with the transit method. Imagine you're trying to detect the brightness change when a planet passes in front of its star. For an Earth-sized planet transiting a Sun-like star, the dimming is about 0.01%. That's 1 part in 10,000. To put this in perspective, imagine you're looking at a car headlight from a mile away, and someone puts a grain of sand in front of it. The dimming you'd see is similar to what we're measuring when we detect an Earth-sized planet transiting its star. Except the star is trillions of miles away, not 1 mile, and you're not just measuring it once. You need to measure it precisely, repeatedly, over months or years to confirm the planet is really there. The Kepler spacecraft, which revolutionized exoplanet detection, could measure stellar brightness to a precision of about 20 parts per million. That's 0.002%. That's the equivalent of measuring the brightness of a light bulb and being able to detect when a single grain of sand passes in front of it. This requires incredibly stable instruments. The spacecraft can't shake or wobble. The detector has to be extraordinarily sensitive. The data processing has to be sophisticated enough to separate real planetary transits from instrumental noise, from star spots, from other stars in the field of view. It's a technical marvel. And Kepler did this for 150,000 stars simultaneously, for years, never stopping, always watching. always measuring. The data it collected is a gold mine that astronomers are still analyzing today. Now, think about the radial velocity method. You're trying to measure the wobble of a star caused by an orbiting planet. For a Jupiter-mass planet orbiting at Jupiter's distance from a Sun-like star, the wobble is about 12 meters per second. That's about 27 miles per hour. The Sun is moving at 27 miles per hour in a circle as Jupiter pulls on it. From 50 light-years away, which is close by astronomical standards, you're trying to measure that 27-mile-per-hour motion. That's like trying to measure how fast a snail is crawling in New York from Los Angeles. But actually, it's harder than that because you're not measuring the star's position. You're measuring its velocity toward or away from you using the Doppler shift of its spectral lines. This requires spectrographs that can measure wavelength shifts to a precision of about 1 part in 10 million or better. The best instruments can detect velocity changes of about 1 meter per second. About walking speed, they can tell if a star 50 light-years away is moving toward or away from us at walking speed. That's the level of precision needed to detect Earth-mass planets at Earth-like distances from their stars. We're not quite there yet for most stars, but we're getting close. The European instrument called Espresso on the Very Large Telescope in Chile can measure radial velocities to about 10 centimeters per second, 4 inches per second. That's the kind of precision that might allow us to detect true Earth analogues around nearby stars. Every advance in precision opens up new territory, allows us to find smaller planets or planets farther from their stars, or both. The technical progress in the last few decades has been extraordinary. It's not just about building bigger telescopes, it's about building more precise instruments, more stable spacecraft, more sophisticated analysis techniques. All of this together has enabled the exoplanet revolution, and it continues to improve. The next generation of instruments will be even more precise, even more capable. The discoveries will keep coming. Now, let me give you a sense of scale for what we've accomplished. The Kepler spacecraft monitored about 150,000 stars in a small patch of sky. This patch covers about 0.25% of the entire sky, 1/400th of the sky. In this tiny region, Kepler found over 2,700 confirmed exoplanets. If you scale this up to the entire sky and assume the rest of the sky is similar, you'd expect to find over 1 million detectable planets. 1 million! And that's just planets that happen to transit from our viewing angle. Remember, only a small percentage of planets are aligned such that they transit. Most planets don't transit from our perspective. So, the real number of planets around those Kepler target stars is much higher than 2,700. It's probably tens of thousands. And those are just the planets around the 150,000 stars Kepler monitored. There are 200 billion stars in our galaxy. If you apply the statistics from Kepler to the whole galaxy, you get numbers in the hundreds of billions of planets. Conservative estimates suggest at least 100 billion planets in the Milky Way. More optimistic estimates go higher, maybe several hundred billion. We've found over 5,000 so far. That's about 0.001% of what's really out there. We've barely scratched the surface. Every planet we've found is a treasure, a window into the diversity of worlds. But They represent an infinitesimal fraction of what exists. The universe is full of planets, more planets than we can ever hope to catalogue individually. But we don't need to find them all. We need to find enough to understand the patterns, enough to see what's common and what's rare, enough to estimate how many might be Earth-like, enough to guide our search for life, and 5,000 confirmed planets is enough to start answering these questions. It's a statistically significant sample. It tells us that planets are ubiquitous, that planet formation is a normal part of star formation, that most stars, if not all, have planetary systems. This is profound. For all of human history until 30 years ago, we didn't know this. We suspected, we hoped, but we didn't know. Now we know. And this knowledge changes how we see the cosmos. We're not special in having planets. We're typical. Earth is one world among countless others. This simultaneously makes us less significant and more connected. Less significant because we're not unique. More connected because whatever we experience here on Earth, birth and death, storms and calms, life and change, all of this is happening on other worlds too. We're part of a grand pattern, a cosmic norm, and there's something beautiful about that. Let me also address the bias in our detections. The planets we've found are not a random sample of all planets. They're biased towards certain types because those are easier to detect. The transit method finds planets that are close to their stars and large enough to cause measurable dimming. So we've found lots of hot Jupiters, hot super-Earths, and close-in planets of various sizes. The radial velocity method finds massive planets, especially close-in massive planets, because they cause larger wobbles. So again, lots of hot Jupiters and massive planets. Direct imaging finds young, massive planets far from their stars because those are self-luminous and easier to see against the star's glare. Microlensing is more democratic. It can find planets at a wide range of distances, but it's limited by the random alignments needed for lensing events. So our catalogue is skewed. It's not representative of all planets. It's representative of the planets we can detect with current technology. As technology improves, as missions run longer, as new techniques are developed, we'll fill in the gaps. We'll find more distant planets, more Earth-sized planets, more planets in the habitable zone. We'll get a more complete picture. But even with the biases, we're learning a lot. We're discovering planet types that don't exist in our solar system. We're seeing orbital configurations we didn't predict. We're finding worlds in environments we thought couldn't host planets. The diversity is staggering. Hot Jupiters, which were the first type of exoplanet found around Sun-like stars, don't exist in our solar system. We have no analog. Jupiter is cold and far from the Sun. Hot Jupiters are roasted and close. How did they get there? They must have formed farther out and migrated inward. This was a surprise. Our theories of planet formation didn't predict this. We had to revise them. Super-Earths, planets larger than Earth but smaller than Neptune, are incredibly common in other star systems. Maybe the most common type of planet, but we don't have any in our solar system. Earth is the largest rocky planet we have, and the next size up is Neptune, which is much larger and made mostly of ice and gas. There's nothing in between, but other stars have planets in that size range. Lots of them. Why doesn't our solar system? We don't know. Maybe it's random chance. Maybe something about the solar system's formation prevented super-Earths from forming here. We're still figuring it out. Mini Neptunes, planets, slightly smaller than Neptune, are also common. Ice giants, smaller than Uranus and Neptune, but larger than Earth. Again, we don't have these in our solar system, but they seem to be everywhere else. There are also planets that orbit two stars at once, called circumbinary planets. Real-life Tatooines, if you're familiar with Star Wars. We didn't know these existed until we found them. Now we've found dozens. And rogue planets, worlds that don't orbit any star at all. They were ejected from their planetary systems during formation and now wander the galaxy alone. We've detected these through micro-lensing. They're hard to find because they're not near any star, so there's no starlight to dim or wobble. But they're out there, possibly billions of them, maybe more rogue planets than stars. The diversity of exoplanets is one of the most exciting aspects of this field. Every new discovery adds to our understanding of what's possible, what nature can create, and it keeps surprising us. Just when we think we've seen everything, we find something new, something strange, something that challenges our theories and forces us to think differently. That's the joy of science. Nature is more creative than we are, and the universe is full of wonders we haven't imagined yet. Now, let me talk about the history of the search in a bit more detail, because the story of how we got here is fascinating. It's a story of persistence, ingenuity, and occasional luck. For decades before the first exoplanet was found, astronomers tried to detect them. They developed techniques, they built instruments, they observed stars, and they came up empty. There were false alarms, claims of detection that were later retracted, signals that turned out to be instrumental artifacts or stellar activity. It was frustrating. The technology wasn't quite good enough. The techniques weren't quite refined enough, but people kept trying. In the 1980s and early 90s, several groups were pushing the limits of radial velocity measurements. They knew that if they could measure stellar velocities to a precision of about 10 meters per second, they could detect Jupiter-like planets. It was a race to see who would get there first. The Swiss team of Meyer and Queloz were using a spectrograph called LODI on a telescope in France. The American teams, including Jeff Marcy and Paul Butler, were using telescopes in California. Both groups were taking data, refining their techniques, searching for the telltale wobbles. Meyer and Queloz got there first. They announced 51 Pegasi b in October 1995. Marcy and Butler confirmed it within days using their own data, and then they found more planets in their existing data. Planets they hadn't recognized before. The floodgates opened. Within a few years, dozens of exoplanets had been found. The field exploded. New groups joined the search. New instruments were built. New techniques were tried. And the count kept rising. The discovery of pulsar planets in 1992 was important, but it was the 1995 discovery of 51 Pegasi b that really launched exoplanet science. That was the moment when we knew for sure that sun-like stars have planets, that planetary systems are not rare, that we're not alone. Since then, the field has matured. It's gone from a fringe topic to a central area of astronomy. Major telescopes and missions are dedicated to exoplanet research. Thousands of astronomers work in the field. It's become mainstream, and the questions have evolved. At first, we just wanted to know if exoplanets existed. Now we want to know what they're like, how they form, how they evolve, which ones might have life. The field has grown from simply detecting planets to characterizing them, to understanding them, to searching for signs of life. This evolution is natural. First, you discover something exists. Then you study it in detail. Then you ask deeper questions. That's where we are now. We're in the detailed study phase. We're characterizing atmospheres, measuring compositions, mapping weather patterns on distant worlds, looking for biosignatures. The next few decades will be incredibly exciting. The discoveries will keep coming, and each one will add to our understanding of planets, of life, of our place in the cosmos. Let me take you even deeper into what makes this discovery so personally meaningful, because numbers and techniques are important, but they don't capture the full impact. Think about what it was like before 1995, before we knew about any exoplanets around normal stars. Science fiction imagined other worlds. Star Trek showed us planets around every star. But in reality, we didn't know. We couldn't point to a specific star and say there's a planet there. We couldn't say with certainty that planets were common. For all we knew, our solar system might have been a cosmic fluke, a rare accident, the only place in the galaxy, maybe the universe, where planets formed. This uncertainty affected how we thought about life. If planets were rare, then life was probably rare. If our solar system was unusual, then maybe Earth was the only habitable world for light years around. Maybe for thousands of light years. Maybe we were alone, not just alone in having intelligent life, but alone in having any kind of life. Alone in having worlds where life could even potentially exist. That's a lonely thought, a frightening thought in some ways. The idea that in all the vastness of space, in all the billions of stars, we might be the only world with oceans and forests and creatures crawling across the land. The only place where evolution created complexity. The only place where consciousness arose. But the discovery of exoplanets changed this. Now we know planets are everywhere. If planets are common, then potentially habitable planets are probably common too. If potentially habitable planets are common, then life might be common. We don't know yet. We haven't found life beyond Earth, but the odds suddenly seem much better. Instead of one lonely world in an empty cosmos, we're one world among trillions. And if life arose here, it could have arisen elsewhere, potentially in millions or billions of places. We don't know the probability of life arising on a suitable planet. Maybe it's high, maybe it's low, but with trillions of planets, even a low probability adds up. Even if only 1 in a million planets develops life, that's millions of living worlds in our galaxy alone. The discovery of exoplanets hasn't just expanded our knowledge, it's expanded our sense of possibility. It's made the universe feel less empty, more full of potential. And that changes how you think about existence, about meaning, about whether we're unique or part of a larger pattern. Personally, I find it comforting. The idea that other worlds exist, that other skies see other sunrises, that rain falls on countless planets, that somewhere out there, perhaps, something is looking up at its sky and wondering the same things we wonder. Are we alone? What's out there? Is there anyone else? The exoplanet revolution has transformed that question from philosophical speculation to scientific inquiry. We can study this now. We can measure. We can observe. We can estimate probabilities. We're not just wondering, we're investigating. And that's powerful. That's what makes science so valuable. It takes questions that humans have asked for millennia and makes them answerable. And exoplanet science is answering questions that go to the heart of who we are and what our place in the universe might be. Now think about your children or future generations. They're growing up in a world where exoplanets are known, where it's common knowledge that other stars have planets. This is normal to them, but for those of us who remember a time before exoplanets were discovered, it's not normal. It's revolutionary. It's a transformation that happened in our lifetimes. We witnessed it. We're living through one of the great revolutions in human understanding. And future historians will mark this era, the late 20th and early 21st centuries, as the time when humanity discovered that planets are ubiquitous. When we went from knowing our solar system alone to cataloging thousands of other worlds. This is comparable to the Copernican revolution, when we realized Earth orbits the Sun rather than being the center of the universe. Or the realization that the Milky Way is just one galaxy among billions. Each of these discoveries made us smaller, but also more aware, more connected to the cosmos, more cognizant of our actual place rather than our imagined centrality. The exoplanet revolution is the latest in this series of humbling but enlightening discoveries. We're not special in having planets. Planets are everywhere. We're typical, not unique. And that's okay. That's more than okay. That's wonderful. Because it means we're part of something larger. Part of a cosmic pattern. Part of a universe rich with worlds. Let me also share what's coming next, because the story is far from over. We're just getting started. The James Webb Space Telescope, which launched in 2021, is revolutionizing exoplanet characterization. Webb observes in infrared, which allows it to study exoplanet atmospheres in unprecedented detail. When a planet transits its star, some of the starlight passes through the planet's atmosphere before reaching us. By analyzing this light, we can detect the chemical signatures of atmospheric gases: oxygen, water vapor, methane, carbon dioxide. Webb can detect these signatures with extraordinary precision. It's already studying the atmospheres of several exoplanets, revealing their compositions, their temperatures, their weather patterns. In the coming years, Webb will observe dozens of potentially habitable planets. It will search for biosignatures, chemical combinations that might indicate life. Oxygen and methane together, for example. Certain organic molecules, patterns that would be hard to explain without biological processes. We might, within our lifetimes, detect signs of life on another world. Not intelligent life necessarily, not radio signals or cities or technology, but simple life, microbes, photosynthetic organisms, something that alters its planet's atmosphere in detectable ways. That would be the discovery of the millennium, the confirmation that life exists beyond Earth, that we're not alone. And it's possible. The technology exists, the planets exist. We're looking, we're searching, and if life is out there and it's left chemical fingerprints in planetary atmospheres, we'll find it. There are also future missions planned specifically for exoplanet detection and characterization. The European Space Agency's Plato mission will launch in the coming years to find and study Earth-sized planets in the habitable zones of Sun-like stars. NASA's Nancy Grace Roman Space Telescope will conduct microlensing surveys to find planets at a wide range of distances from their stars. Ground-based telescopes are getting more powerful. The extremely large telescope under construction in Chile will be able to directly image exoplanets and study their atmospheres. These next-generation instruments will take exoplanet science to new heights. They'll find more planets, smaller planets, planets more like Earth. They'll characterize atmospheres in detail. They'll search for life. The next few decades will be extraordinary. We're living at the dawn of this field. We're the first generation to know about exoplanets, and we're the generation that might discover life beyond Earth. That's a privilege, a gift, a moment in history that you're part of whether you realize it or not. So, when I tell you we've found over 5,000 exoplanets, I'm not just reciting a number. I'm inviting you to appreciate what that number represents. A revolution in knowledge, a transformation in how we see ourselves, a window into the diversity and abundance of worlds beyond our own. Every single one of those 5,000 planets is a world. A place with a horizon and a sky, with gravity pulling on its surface, with starlight warming its atmosphere or its rocks, with its own unique characteristics and history. Some are scorching hot, some are frozen, some have thick atmospheres, some have none. Some might have oceans, some might have life. Each one is different. Each one is real. Each one is out there right now, orbiting its star, existing whether we observe it or not. And we're learning about them. We're studying them. We're adding them to our catalogue of knowledge. This is humanity at its best, curious, persistent, creative, pushing boundaries, answering questions, expanding our understanding of the cosmos. And you're part of this by learning about exoplanets, by appreciating what's been discovered, by understanding that the universe is full of worlds. You're participating in this revolution. You're part of the generation that knows, that understands, that sees the cosmos not as empty space between stars, but as a place filled with planets, filled with worlds, filled with possibility. That's what the exoplanet revolution gives us. Not just data and numbers, but perspective. Not just scientific knowledge, but cosmic awareness. Not just information about other worlds, but insight into our own place among them. What strikes me most about the diversity we've found is how it shatters our assumptions. When scientists first theorized about exoplanets, they imagined miniature versions of our solar system, rocky planets close in, gas giants farther out, nice orderly arrangements. But nature had other plans. Take mini-Neptunes. These worlds between Earth and Neptune in size make up roughly 30 to 40% of all the planets we've discovered. They're probably the most common type of planet in the galaxy. Yet, we don't have a single one in our solar system. Earth is about 13,000 kilometers in diameter. Neptune is about 50,000, but there's nothing in between. No intermediate-sized worlds. Other star systems are full of them, planets 2 to 4 times Earth's size. Too big to be rocky like Earth, too small to be gas giants like Jupiter. Something in between. Probably rocky cores wrapped in thick hydrogen and helium envelopes. Or maybe water worlds with deep global oceans. We're still figuring out their compositions. These worlds challenge our theories because we don't understand why our solar system lacks them. Was it random chance? Did Jupiter's gravity prevent them from forming here? Did they form and then get destroyed or ejected? We're not sure, but their abundance elsewhere tells us that our solar system, the template we've studied for centuries, is not typical. It's just one configuration among many. Super-Earths present similar mysteries. These are rocky planets larger than Earth, but not quite Neptune-sized, maybe 1.5 to 2 times Earth's diameter, 2 to 10 times Earth's mass. We've found hundreds of them. They orbit close to their stars, usually with periods of days to weeks. Their surfaces are probably scorching hot, but they exist. They're stable, they're common, and we don't have any. Earth is the largest rocky planet in our solar system. Mars is smaller. Venus is nearly Earth-sized, but slightly smaller. Mercury is tiny. Then you jump to the ice giants, Uranus and Neptune, which are much larger. There's this gap where super-Earths would fit, a gap filled in other systems but empty in ours. This makes you wonder what else might be common in the galaxy but absent from our local neighborhood. What are we missing by only studying our own system? How unrepresentative is our experience? Then there are the truly bizarre worlds. Planets so strange they seem like science fiction. Tidally locked planets that keep one face always toward their star, one hemisphere in perpetual daylight, scorched and molten, the other in eternal darkness, frozen solid, with a narrow twilight band between where temperatures might be tolerable, planets with winds that scream at thousands of kilometers per hour, with temperatures hot enough to vaporize metals, with atmospheres made of silicate vapor that rains liquid glass sideways in supersonic winds. We've detected these conditions on hot Jupiters through atmospheric spectroscopy. When starlight passes through a planet's atmosphere during a transit, different molecules absorb different wavelengths. By analyzing which wavelengths are absorbed, we can identify what's in the atmosphere. Sodium, potassium, water vapor, carbon monoxide, even titanium oxide on some of the hottest worlds. And from these chemical signatures, we can infer conditions. Hot Jupiters with day-side temperatures exceeding 3000 Kelvin, hot enough to melt iron, hot enough to dissociate molecular hydrogen into atomic hydrogen. These aren't just hot, they're hellish, but they're real, they exist, and studying them teaches us about atmospheric physics in extreme conditions. Some planets orbit their stars backwards, retrograde orbits. They go the opposite direction from the star's rotation. This shouldn't happen according to standard planet formation theory. Planets should form in disks that rotate with the star. They should orbit in the same direction, but some don't. Something in their history caused their orbits to flip. Maybe gravitational interactions with other planets. Maybe close encounters that exchanged angular momentum. We're still working out the dynamics, but it happens. And it tells us that planetary systems can be chaotic, that planets can migrate, that orbits can change dramatically over time. Our solar system appears relatively stable. The planets have been in roughly their current orbits for billions of years. But this might be unusual. Other systems might be more dynamic, more violent, planets moving inward or outward, ejecting each other, colliding, creating the configurations we observe. Water worlds are another fascinating possibility. Planets that are entirely covered by global oceans, no continents, no dry land, just water, potentially hundreds of kilometers deep. We haven't confirmed any of these yet, but some of the planets we've found have densities suggesting they could be water-rich. Not just water on the surface like Earth's oceans, but substantial fractions of their mass being water. Maybe 20 to 50% water by mass compared to Earth's less than 1%. Imagine a world where the ocean is so deep that the pressure at the bottom creates exotic forms of ice. High-pressure ice phases that exist only deep underwater. Ice that's hot, strange physics, strange geology, strange possibilities for life. Would life in a global ocean be different from life on Earth? Would it be simpler because there's no land to colonize? Or more complex because the ocean provides three-dimensional habitat? We don't know, but we might find out. Lava worlds exist close to their stars, planets so close that their surfaces are molten rock, oceans of lava, atmospheres of vaporized rock, temperatures exceeding 2000 Kelvin. These worlds complete orbits in hours, less than a day. They're being cooked by stellar radiation. Their surfaces glow red hot, visible to telescopes. We can actually see their thermal emission. Watch as the hot side rotates into view and the planet appears to brighten, then dims as the cooler side rotates into view. These observations let us map temperature variations across the planet. See how heat is distributed. Understand atmospheric circulation. It's remarkable that we can learn this much about worlds so far away. Iron planets might exist too. Planets where the rocky mantle has been stripped away, leaving just the metallic core. This could happen if a planet suffers a giant impact that blasts off the lighter rock, leaving the dense iron core behind. Or if tidal forces from a close star strip away the mantle. These worlds would be small for their mass. Extremely dense, metallic surfaces, maybe even molten iron oceans. Magnetic fields stronger than anything in our solar system. Pure speculation at this point, but possible, and if they exist, we might be able to detect them through their unusual density. Puffy planets defy expectations in the opposite direction. These are gas giants with densities lower than Saturn's, lower than water in some cases. Inflated atmospheres that make them huge but not massive. We're not sure why they're so puffy. Maybe tidal heating from their stars. Maybe heat from their interiors that hasn't escaped yet. Maybe something about their atmospheric composition. But they exist. We've found dozens, and they challenge our understanding of planetary structure. Frozen worlds dominate the outer regions of planetary systems, planets beyond the ice line where water freezes. These might be common, but hard to detect because they're far from their stars. They don't transit frequently. They cause small wobbles. They're cold and dim, making direct imaging difficult. But they're probably numerous, maybe more common than the close-in planets we've been finding. Statistical analysis suggests that cold giant planets like Jupiter and Saturn are widespread. And if those exist, smaller ice planets probably do too. Analogues to Uranus and Neptune. Worlds with thick atmospheres of hydrogen and helium over icy mantles and rocky cores. We're just beginning to find these because they require long observation campaigns, years of data to detect their slow orbits. Rogue planets drift through interstellar space, unbound to any star. These formed in planetary systems, but were ejected by gravitational interactions, maybe during the chaotic early phases of system formation when planets migrate and compete for stable orbits. Some calculations suggest rogue planets might outnumber stars, that there could be billions or trillions of them in our galaxy alone, wandering in the darkness between stars, cold, frozen, dead. Some might retain internal heat for billions of years, heat from radioactive decay or residual formation heat. These might have subsurface oceans beneath icy crusts, liquid water maintained by internal heat rather than starlight. Could life exist in such oceans, cut off from any star, dependent entirely on internal energy? It seems unlikely, but not impossible. And if rogue planets are as common as we think, there could be countless such worlds. The atmospheres we're detecting reveal chemistry happening in real time. Photochemistry driven by starlight, molecules being created and destroyed. On some hot Jupiters, we've detected carbon monoxide and carbon dioxide, water vapor, methane. The ratios tell us about temperature and chemistry, whether the atmosphere is in chemical equilibrium or being driven away from equilibrium by stellar radiation. On cooler planets, we might eventually detect more Earth-like atmospheres: oxygen, nitrogen, water. The challenge is that most of the planets we can study atmospherically are large and close to their stars. Hot Jupiters and super-Earths. The atmospheres of smaller, more temperate planets are harder to analyze because the atmospheric signal is weaker. But the James Webb Space Telescope is changing this. Webb's infrared capabilities allow it to probe atmospheres with unprecedented detail. It's finding molecules we couldn't detect before, seeing structures in atmospheric composition, mapping temperature variations. Over the next decade, Webb will observe dozens of potentially interesting planets, and will learn what their atmospheres are really like. The possibility of biosignatures drives much of this research. If we can detect oxygen and methane together in a planet's atmosphere, that might indicate life. On Earth, oxygen is produced by photosynthesis. Methane is produced by biological processes. In the absence of life, these gases would react and disappear. Their simultaneous presence suggests something is replenishing them. Maybe life. Of course, there could be non-biological explanations. Geological processes that produce both gases. Photochemistry driven by stellar ultraviolet light. We'd need to rule these out before claiming detection of life, but the signature would be compelling, worth investigating. And if we detect it, we'll launch follow-up observations, get better data, try to understand what's really happening on that distant world. Phosphine in Venus's atmosphere caused excitement recently. On Earth, phosphine is produced primarily by microbes. Finding it in Venus's atmosphere raised the possibility of life floating in the clouds. Above the hellish surface where temperatures are hot enough to melt lead, up in the clouds where temperatures are more moderate, where conditions might be survivable. The detection was controversial. Other teams questioned whether phosphine was really there or if the signal was from something else. The debate continues, but it shows how seriously we take potential biosignatures, how willing we are to consider life in unexpected places, and how careful we need to be before making extraordinary claims. The exoplanets we've found cluster around certain types of stars. Most orbit red dwarfs, small cool stars that are the most common type in the galaxy. Red dwarfs are long-lived. They burn their fuel slowly. They'll survive for trillions of years, much longer than sun-like stars. And they're abundant. About 70 to 80% of stars in our galaxy are red dwarfs. If most red dwarfs have planets, that means billions upon billions of worlds orbiting these small stars. Some of these planets are in the habitable zone where temperatures might allow liquid water. Proxima Centauri, B, the closest exoplanet to Earth, orbits a red dwarf just 4 light-years away. It might have liquid water, might be habitable, we don't know yet. But it's close enough that future missions might be able to study it in detail, maybe even send probes someday. Though that's far in the future, red dwarf planets face challenges. These stars are active, they flare, they emit intense ultraviolet and X-ray radiation. This could strip away planetary atmospheres, sterilize surfaces, make life difficult or impossible. Also, to be in the habitable zone of a red dwarf, a planet must orbit very close, so close that tidal forces lock it. One side always faces the star, one side always dark. This creates extreme temperature differences, howling winds as air tries to flow from hot to cold. Maybe not ideal for life, but maybe life could adapt, could find niches in the twilight regions, could exist in subsurface oceans protected from radiation. We don't know, but we're learning. Red dwarf planets are a major focus of current research. Sun-like stars host planets too. Many of the systems Kepler studied were around G-type stars similar to our Sun. We've found hot Jupiters around these stars, super-Earths, mini-Neptunes, a whole zoo of worlds. Some Sun-like stars have multiple planets. Compact systems with 3, 4, 5 planets, all orbiting closer than Mercury orbits our Sun. Packed in tight, stable somehow, despite their proximity. Other systems have planets spread out like ours, resembling the solar system's architecture, wide spacing, mixture of planet types. But even these systems often have surprises, planets in unexpected orbits, configurations we didn't predict. Larger stars, A-type and F-type stars, also have planets. These stars are hotter and more massive than the Sun. They evolve faster. They don't live as long. And detecting planets around them is harder because these stars rotate quickly and have fewer spectral lines for radial velocity measurements. But we've found planets there too, often massive planets, Jupiter-sized or larger. These discoveries tell us planet formation works around a wide range of stellar masses. It's not limited to Sun-like stars. Even binary star systems have planets, stars that orbit each other in pairs. Planets can orbit one star in the binary, staying close to it, or they can orbit both stars in a wide circumbinary orbit. Both configurations exist. We've found examples of each, Tatooine-like worlds where two suns rise and set, strange dynamics, complex gravitational interactions, but stable. Nature figures out how to make it work, and this is important because most stars are in binary or multiple star systems. If planets can form and survive in binaries, that dramatically increases the number of potential habitats in the galaxy. The architectures of planetary systems vary wildly. Some systems are tightly packed, planets orbiting in resonances where their orbital periods have simple integer ratios. 2:1, 3:2. These resonances stabilize orbits, prevent close encounters, allow planets to coexist in close proximity. Other systems are sparse, planets widely separated, lots of empty space between them. Some systems are flat, all planets orbiting in nearly the same plane like our solar system. Others are tilted, planets with inclined orbits, some even perpendicular to each other. This diversity suggests that planet formation and evolution are influenced by many factors. Initial conditions in the protoplanetary disk, interactions between planets, migration driven by disk interactions or gravitational scattering, perturbations from nearby stars. All of these shape the final configuration, and the result is enormous variety. Orbital eccentricities add another dimension. Our solar system's planets have nearly circular orbits, but many exoplanets have highly elliptical orbits. Their distances from their stars change dramatically over the course of an orbit. Close approach, then far swing, then close again. This creates extreme seasonal variations. The planet's temperature and radiation environment fluctuate wildly. What drives these eccentric orbits? Probably gravitational interactions, planet-planet scattering, multiple planets forming close together. Eventually they interact. One or more gets ejected. The survivors end up in eccentric orbits. Or sometimes a companion star in a wide binary causes perturbations that increase eccentricity. Whatever the mechanism, eccentric orbits are common, and they change the possibilities for climate and habitability. A planet with eccentric orbit might spend most of its time too cold or too hot for liquid water, only briefly passing through habitable temperatures, making life harder to sustain. Multi-planet systems are common. We've found hundreds of stars with 2, 3, 4 or more planets. The Kepler data suggests multi-planet systems are actually more common than single-planet systems. Most stars probably have multiple planets, even if we can only detect 1 or 2. This makes sense. Planet formation happens in disks. Disks have material at different distances. Multiple planets should form, but the number and configuration depend on details. How much mass was in the disk, how the disk evolved, how planets migrated, how they interacted. Sometimes you get a system like ours, 8 planets spread across a wide range of distances. Sometimes you get a compact system with 7 Earth-sized planets, all closer than Mercury, like TRAPPIST-1, a red dwarf system where 7 planets orbit in tight resonances, at least 3 in the habitable zone. A completely different architecture from ours, but stable, functioning, existing. TRAPPIST-1 deserves special mention. It's one of the most exciting systems we've found. 7 planets, all roughly Earth-sized. 3 potentially habitable, orbiting a red dwarf 40 light-years away. The planets are so close together that if you stood on one, you'd see the others as large disks in the sky. Bigger than the Moon appears from Earth. Eclipses would be common. The view would be spectacular. These planets are close enough and interesting enough that they're prime targets for atmospheric characterization. Webb is studying them now, looking for signs of atmospheres, water vapor, carbon dioxide, maybe something unexpected. This system might teach us more about habitability around red dwarfs than any other. It's a laboratory for studying planets in extreme proximity to their star and to each other. Another fascinating system is Kepler-90. This star has at least 8 planets, tying our solar system for the most known planets around a single star. The system is compact. All 8 planets orbit closer than Earth orbits the Sun, yet they've been stable for billions of years. How? Resonances, probably. Careful orbital arrangements that prevent collisions. Nature finding ways to pack planets into small spaces. The discovery shows that high planet multiplicity is possible, that systems can be dense yet stable, that our assumptions about spacing might be too conservative. The demographics of exoplanets are starting to emerge from the data. Small planets are common, maybe outnumbering large planets by a factor of 3 or 4. The exact ratio depends on how you define size cutoffs. But clearly, rocky and ice planets are more numerous than gas giants. This makes sense. Rocky planets require less mass to form. Gas giants need to gather huge amounts of hydrogen and helium. They need to form before the disk dissipates. Rocky planets can form anytime there's solid material. So, finding more small planets than large is expected, but confirming it observationally required detecting small planets, which is harder. The fact that we've now found hundreds of Earth-sized and super-Earth-sized planets tells us they're abundant. Probably the dominant planet type in the galaxy. The habitable zone is where conditions might allow liquid water on a planet's surface. Not too hot, not too cold. For Sun-like stars, the habitable zone is roughly between Venus's orbit and Mars's orbit. About 0.9 to 1.5 astronomical units. For red dwarfs, the zone is much closer because the stars are cooler. Maybe 0.1 to 0.2 AU, for hotter stars farther out. The zone's width depends on stellar luminosity and planetary atmosphere. A thick greenhouse atmosphere can warm a planet that would otherwise be too cold. A thin atmosphere or high reflectivity can cool a planet that would otherwise be too hot. So the habitable zone is approximate, but it's a useful concept for identifying potentially interesting planets. We've found dozens of planets in habitable zones, but being in the zone doesn't guarantee habitability. You need the right atmosphere, the right atmospheric pressure, water, stable climate, Plate tectonics maybe to recycle carbon and maintain long-term climate stability. Protection from stellar flares if it's a red dwarf. Magnetic field to shield from radiation. Lots of factors. Just being the right distance from the star is necessary but not sufficient. Still, it's a start. And the planets we've found in habitable zones are targets for detailed study, for atmospheric characterization, for searching for biosignatures. These are the worlds where we might find life. Estimates for the number of potentially habitable planets in our galaxy vary. Conservative estimates suggest tens of billions. More optimistic estimates go higher, maybe 100 billion or more. The uncertainty comes from definitions. What counts as habitable? Just liquid water? Or do you need plate tectonics, magnetic field, stable climate, low stellar activity? The more requirements you add, the lower the number. But even conservative estimates give billions of worlds. That's extraordinary. Billions of places where life might exist, where conditions might be suitable. We haven't detected life on any of them yet, but the potential is staggering. The search for life focuses on biosignatures, chemical or physical signs of biological activity. Oxygen is a strong biosignature because it's reactive. It shouldn't persist in an atmosphere unless something is producing it. On Earth, photosynthesis produces oxygen. Without life, Earth's oxygen would disappear in a few million years. So, detecting oxygen on an exoplanet would be significant, especially if combined with other gases like methane or nitrous oxide. But there are false positives. Photodissociation of water vapor by ultraviolet light can produce oxygen without biology. You need to rule out these alternatives before claiming life. This requires detailed atmospheric models, understanding the planet's star, its radiation environment, its atmospheric chemistry. It's complex, but doable. Other potential biosignatures include phosphine, ammonia, methyl chloride, gases produced by life on Earth but rare abiotically. Detecting these would be interesting, suggestive, but again, you'd need to understand the context. Is there a geological source? Can atmospheric chemistry produce them? Biosignature detection will be a process of elimination, ruling out non-biological explanations until biology is the best remaining hypothesis. And even then, you'd want multiple lines of evidence, multiple biosignatures, patterns in atmospheric composition that are hard to explain without life. This is careful science. It'll take time, lots of observations, detailed analysis, but it's the path forward. Technosignatures are another approach. Instead of looking for life's chemical fingerprints, look for signs of technology, radio signals, laser pulses, artificial structures around stars. This is SETI, the search for extraterrestrial intelligence. It's been going on for decades with no confirmed detections. But the search continues because finding intelligent life would be transformative. It would mean we're not alone, not just in having life, but in having consciousness, technology, civilization, and it would open possibilities for communication, learning from another species, understanding different paths of development, different solutions to problems, different perspectives on existence, even negative results are informative. Silence tells us intelligent technological civilizations are either rare, short-lived, or not broadcasting. All of these possibilities have implications for our own future. The Drake equation attempts to estimate the number of communicating civilizations in our galaxy. It multiplies factors like star formation rate, fraction of stars with planets, number of habitable planets per system, fraction where life arises, fraction where intelligence develops, fraction that develop technology, and how long civilizations survive. Each factor is uncertain, some very uncertain. But the exoplanet discoveries have nailed down the early factors. Stars do have planets. Habitable zone planets exist. These are no longer unknowns, they're certainties. The remaining uncertainties are about life and intelligence. How often does life arise? We only have one example, Earth. So we can't estimate the probability. It might be high, might be low. We don't know. How often does intelligence arise from life? Again, one example. We can't estimate. How long do technological civilizations last? We've lasted a few thousand years depending on how you count. We don't know if we'll last another 1,000 or 1,000,000. So the Drake equation remains speculative. But at least now we know planets are common. That's progress. The Fermi paradox asks where everyone is. If life is common, if intelligence is common, if the galaxy is old and vast, why haven't we detected anyone? Why isn't there evidence of galactic civilizations, megastructures, von Neumann probes, something? The silence is eerie. Various solutions have been proposed. Maybe intelligent life is rare. Maybe it self-destructs quickly. Maybe interstellar travel is harder than we think. Maybe advanced civilizations hide intentionally. Maybe they're here, but we can't recognize them. Maybe we're early. Maybe intelligence only recently became possible in the universe's history, and we're among the first. Each explanation has problems. The paradox remains unsolved, but the discovery of billions of planets makes it more pressing, more puzzling. With so many worlds, why so much silence? Some argue we're searching wrong, that we're looking for our kind of life, our kind of technology, that alien civilizations might be so different we wouldn't recognize them. This is possible, but we have to start somewhere. We search for what we know: carbon-based life, water as a solvent, chemical biosignatures we understand, radio signals we can detect. As our capabilities expand, we can search for more exotic possibilities. But you can't search for everything at once. You prioritize. You look for the most likely scenarios first. And so far, those searches have found nothing, which is interesting in itself. The exoplanet catalog will keep growing. Current missions will find thousands more. Future missions will push into new parameter space, finding smaller planets, more distant planets, planets around fainter stars. We're developing techniques to directly image Earth-like planets around nearby stars, to block the star's light precisely enough that we can see the planet, to collect enough photons from the planet to get a spectrum, to identify atmospheric gases, to map surface features maybe, seeing oceans, continents, clouds, seasons. This is decades away but possible. The technology is being developed: coronagraphs, star shades, extremely large ground-based telescopes with adaptive optics, space telescopes designed specifically for exoplanet imaging. Each advance brings us closer to answering the big questions. Are we alone? Is Earth unique? Is life common? The economic and societal impact of discovering life would be immense. It would affect religion, philosophy, science, culture, how we see ourselves, our place in the universe, our significance. Some argue it would be destabilizing, that many people would struggle to accept it. Others argue it would be liberating, that it would unite humanity around our common identity as one species among many, that it would shift focus from petty conflicts to larger questions. We don't know how society would respond, but it would be one of the most important discoveries in human history, comparable to the Copernican revolution or the discovery of evolution, a fundamental shift in perspective. And it's possible it'll happen in our lifetimes. Not guaranteed, but possible. We're looking in the right places with the right tools. If life is out there leaving detectable signatures, we have a chance of finding it. Funding these missions requires sustained commitment. Space telescopes cost billions. Take decades to plan, build, and operate. Ground-based surveys need dedicated telescope time. Data analysis requires researchers and computing resources. All of this costs money, and priorities compete. Should we spend billions searching for life on exoplanets, or solving problems on Earth? This debate is ongoing, but I'd argue both are important. Understanding our place in the universe has value, not just practical value, intellectual and philosophical value. And the technologies developed for space exploration often find applications on Earth. Detectors, imaging techniques, data analysis methods, machine learning algorithms trained on exoplanet data. These spill over into other fields: medicine, materials, science, computing. The benefits are diffuse but real. Public interest in exoplanets is high. People care about this. Articles about exoplanet discoveries get read. Documentaries get watched. Talks get attended. There's something universal about wondering what's out there, whether we're alone, what other worlds are like. This curiosity is part of being human. It's driven exploration throughout history, to new continents, across oceans, into space, now to other stars. And that journey is just beginning. We've found thousands of worlds, but we've barely begun to understand them. Each one is unique. Each one has stories to tell about how it formed, how it evolved, what it's like now, and potentially whether life exists there. The strange thing about exoplanet discoveries is how quickly they've become normal. 30 years ago, finding a planet around another star would have been front-page news for weeks. Now, we announce new discoveries regularly, and they barely register. Dozens of planets confirmed every few months. It's routine. But this familiarity shouldn't diminish the wonder. Each planet is a world, a place, real, existing, orbiting its star whether we observe it or not, with its own characteristics, its own history, its own future. The fact that planets are common doesn't make them less amazing. It makes the universe more amazing. It shows how creative nature is, how full of possibilities, how rich with worlds beyond counting. The statistical methods used to analyze exoplanet data are sophisticated. When Kepler observes a brightness dip, algorithms must distinguish real transits from false positives. Instrumental glitches, star spots, binary star eclipses masquerading as transits, background stars contaminating the signal, all of these can mimic planetary transits. So, astronomers developed machine learning techniques to vet candidates, training algorithms on known planets and known false positives, teaching computers to recognize patterns, to identify which signals are likely real. This vetting process is crucial. Without it, the candidate lists would be full of false alarms. With it, we achieve confirmation rates of 80 to 90% for high-quality candidates. The algorithms get better with more training data, and as we confirm more planets, we train the algorithms better. It's a virtuous cycle, improving our ability to find smaller planets with weaker signals. Follow-up observations confirm candidates. When Kepler or TESS finds a candidate, ground-based telescopes observe it, looking for the transit with their instruments, confirming the signal is real, measuring radial velocity if possible to get the planet's mass, checking for contamination from nearby stars, ruling out alternative explanations. This follow-up work is time-consuming. It requires dedicated telescope time, skilled observers, careful analysis, but it's essential. Confirmation turns candidates into known planets, adds them to the official catalogues, makes them subjects for further study. The nomenclature system for exoplanets is straightforward but can get confusing. Planets are named after their star, followed by a lowercase letter. The first planet discovered around a star gets B, the second gets C, and so on. The letter A is reserved for the star itself, though it's rarely used. So 51 Pegasi b is the first planet found around 51 Pegasi. Kepler 186f is the sixth object in the Kepler 186 system, meaning it's the fifth planet since the star is A. But the lettering doesn't indicate orbital distance. It indicates discovery order, so the letters don't necessarily go in order from the star outward. This can be confusing, but that's the convention. And with thousands of planets, keeping track requires databases. Catalogs that list every confirmed planet, their properties, discovery methods, references to papers, all maintained by organizations like the NASA Exoplanet Archive. These resources are invaluable for researchers and educators. Collaborations between space-based and ground-based observations maximize science return. Space telescopes find candidates. Ground telescopes confirm and characterize them. Large ground telescopes with adaptive optics can measure radial velocities with high precision, can get spectra that space telescopes can't, can observe targets continuously for hours without Earth's rotation interrupting. Meanwhile, space telescopes avoid atmospheric interference, can monitor thousands of stars simultaneously, can detect tiny brightness changes impossible from the ground. The synergy is powerful. Missions like Kepler and TESS find the planets. Telescopes like Keck, Gemini, VLT follow up. Together, they build the catalogue and our understanding. Population statistics reveal trends invisible in individual cases. When you have thousands of planets, you can ask statistical questions. How does planet occurrence depend on stellar mass, on stellar metallicity, on position in the galaxy? What's the typical spacing between planets in multi-planet systems? How common are resonant configurations? What's the mass distribution of planets? The radius distribution? These questions require large samples. And now we have them. The answers are shaping our theories, showing us that planets are robust, that they form efficiently around stars of many types, that small planets dominate, that multi-planet systems are typical. Each statistical result constrains models of planet formation and evolution, helps us understand which processes are important, which predictions were right, which need revision. Comparative planetology takes on new meaning with exoplanets. We can now compare thousands of worlds, look for patterns, relationships between properties. Does planet density correlate with stellar metallicity? Does it depend on distance from the star? What's the relationship between planet radius and mass? These aren't just academic questions. They tell us about composition, about how planets form, about what determines whether a planet ends up rocky or gaseous. And the answers sometimes surprise us. The radius-mass relationship has a gap. Planets between about 1.5 and 2 Earth radii are less common than expected. This is called the Radius Valley or Fulton Gap. It might indicate a transition between rocky super-Earths and gaseous mini-Neptunes. Planets that couldn't accrete or retain hydrogen envelopes end up below the gap. Planets that could end up above it. The gap teaches us about atmospheric loss, about how stellar radiation can strip atmospheres from smaller planets, about the physics governing planet composition. The metallicity connection intrigues astronomers. Stars with higher metallicity, meaning more elements heavier than hydrogen and helium, are more likely to host giant planets. This makes sense. Giant planets need solid cores to form, cores made of ice and rock. Higher metallicity means more solids available in the protoplanetary disk, more material to build cores. So giant planet formation is easier. The correlation is strong, well established. But small planets show less dependence on metallicity. They form around metal-poor stars almost as readily as around metal-rich stars. This suggests different formation pathways, different requirements. Giant planets need lots of solids. Small planets can form with less. Understanding these dependencies helps us predict where different types of planets should exist, guides our search strategies. Planet migration remains a major topic of research. Hot Jupiters couldn't form where they are, too close to their stars. Too hot, the gas needed to build them would have been blown away by stellar radiation before they could grow large. So they must have formed farther out where it was cooler, then migrated inward. How? Two main mechanisms. Type Y and Type 2 migration involve interactions with the protoplanetary disk. The disk's gravity pulls on the planet, creates torques that cause the planet to spiral inward or outward depending on disk properties. Or gravitational scattering, multiple planets forming in the same system. Eventually, they interact. Orbits become unstable. one planet gets flung inward on an eccentric orbit. Tidal forces from the star then circularize the orbit, leaving a hot Jupiter close in. Both mechanisms probably operate. Some hot Jupiters formed via disk migration, others via scattering. Determining which mechanism dominated in individual cases is challenging, but both reshape planetary systems dramatically. The NICE model revolutionized thinking about our solar system's history. Named after the city in France where it was developed, it proposes that the giant planets formed more compactly. Jupiter, Saturn, Uranus, Neptune all closer together than today. Then orbital resonances caused migration. Jupiter moved inward slightly. Saturn moved outward. Uranus and Neptune moved far outward. This migration scattered planetesimals, caused the late heavy bombardment, cleared the asteroid belt, established the current configuration. The model explains many features of the solar system that were previously mysterious, and it shows that even our system wasn't static. Even here, planets migrated, orbits changed. The configuration we see now is the result of billions of years of evolution, not the initial state. This perspective applies to exoplanet systems too. What we observe is a snapshot, a moment in ongoing evolution. Planets might still be migrating, systems might still be settling. What looks stable now might change over millions or billions of years. Resonances play huge roles in system stability. When two planets have orbital periods in simple ratios like 2:1 or 3:2, they're in resonance. Their gravitational interactions reinforce at regular intervals. This can stabilize orbits, prevent close encounters, allow planets to coexist despite proximity. Many exoplanet systems show resonant chains, multiple planets all locked in resonances with their neighbors. These configurations are remarkable. They require special formation conditions. Probably the planets migrated inward together through the disk, captured into resonances as they moved. Then the disk dissipated, leaving them locked. Resonant systems are laboratories for studying dynamics, testing models, understanding how gravity shapes orbital evolution. Instabilities destroy systems or reshape them dramatically. Not all planetary systems are stable long-term. Some go through phases of instability. Planets scatter off each other. One or more gets ejected, becomes a rogue planet wandering interstellar space. Others collide, merge, or get pushed into the star and are destroyed. These violent events leave signatures, high orbital eccentricities, missing planets, unusual configurations. By studying the survivors, we infer the violence that shaped them, and simulations show instabilities are common in system formation. Many systems start with more planets than they end with. The survivors are the lucky ones, those whose orbits happen to avoid close encounters, whose configurations were stable enough to persist. This selection effect means observed systems are biased towards stable configurations. Towards survivors, the unstable systems destroyed themselves early and aren't here to be observed. Collisions between planets can create unusual outcomes. If two rocky planets collide, they might merge, forming a larger planet, or fragments might be ejected, becoming asteroids or smaller moons. If a giant planet collides with a rocky planet, the rocky planet might be shredded, its material incorporated into the giant's core or atmosphere. These collisions release energy, melt surfaces, create magma oceans, drive atmospheric loss. The Moon likely formed from a giant impact between Earth and a Mars-sized object. This impact melted both bodies, ejected material into orbit around Earth. That material coalesced into the Moon. We suspect similar impacts happened around other stars, creating unusual moons, debris disks, modified planets with compositions different from what simple formation models predict. The exoplanet mass-radius relationship reveals composition. For a given mass, different compositions produce different radii. Pure iron planets would be small and dense. Pure water planets would be large and less dense. Rocky planets intermediate. By measuring both mass and radius, we constrain composition, and we find enormous diversity. Some planets are denser than Earth, maybe iron-rich. Others are puffier, maybe water-rich or with thick hydrogen atmospheres. The relationship isn't a single line, it's a cloud of points. Each planet finding its place based on its unique composition and structure. And outliers exist. Planets that don't fit trends, that demand explanation. Maybe unusual formation histories, maybe atmospheric loss, maybe tidal heating inflating them. Each outlier teaches us something about the range of possibilities. Atmospheric escape shapes planetary evolution. Small planets with weak gravity can lose their atmospheres over time. Stellar ultraviolet radiation heats the upper atmosphere, gives atoms enough energy to escape. Over billions of years, this can strip a planet bare, turn a mini Neptune into a rocky core, create a super-Earth. This process is called photoevaporation, and evidence suggests it's common. The radius valley might result from photoevaporation. Planets below the valley lost their atmospheres. Planets above retained them. The transition happens around certain masses and stellar irradiations. We're testing these models by looking for planets in transition, worlds currently losing their atmospheres, finding extended envelopes of escaping gas. These observations confirm photoevaporation operates, shapes the planet population we observe. Magnetic fields protect planets from atmospheric loss. Earth's magnetic field deflects solar wind, prevents it from stripping our atmosphere directly. Mars lost its magnetic field early, and its atmosphere was gradually stripped, leaving the thin atmosphere we see today. For exoplanets, we can't measure magnetic fields directly yet, too far away, but we can infer their importance. Planets with strong fields should retain atmospheres better. Planets without might lose them. Understanding magnetic field generation requires knowing a planet's interior, its core composition, its rotation rate, all hard to measure for distant worlds. But theory suggests massive planets and those with molten cores generate fields. Smaller planets might not. This affects habitability. A planet in the habitable zone might still be uninhabitable if it lacks a magnetic field and its atmosphere is stripped. Tidal heating can make planets habitable outside the traditional habitable zone. Europa and Enceladus in our solar system have subsurface oceans maintained by tidal heating, not by sunlight. Exoplanets in tight orbits or eccentric orbits experience tidal heating. This could melt ice, create subsurface oceans, enable life even far from the star where surface temperatures are freezing, expanding the habitable zone concept. Instead of just a range of distances from the star, habitability becomes a function of distance, orbital eccentricity, planetary mass, internal structure. More complex, but more comprehensive. And it means more planets might be habitable than simple models suggest. Surface conditions on exoplanets span extremes beyond imagination. Lava worlds with molten surfaces, ice worlds with surfaces colder than any natural place on Earth, tidally locked worlds with permanent day and night sides, high-pressure worlds where the atmosphere is so thick it transitions continuously into ocean with no defined surface, low-pressure worlds where water boils at room temperature. Each environment presents unique challenges for life if it exists, but also unique opportunities. Life adapts, finds niches. On Earth, it exists in boiling hydrothermal vents and freezing Antarctic lakes, in acid and base, in radiation-soaked environments. If life can adapt to such extremes on one planet, maybe it can adapt to extremes on others. Maybe the diversity of planetary environments means a diversity of potential biospheres, each adapted to its own world. This is speculative but motivating. It keeps us searching, keeps us wondering what might exist on these strange worlds. The observational programs targeting exoplanets are incredibly ambitious. Ground-based surveys like the Mirth project monitors thousands of nearby red dwarfs looking for transiting planets. Automated, running every clear night. WASP and KELT surveys use small, wide-field telescopes to search bright stars for transits, complementing space missions by targeting stars too bright for Kepler or TESS. High-precision radial velocity programs on the largest telescopes push toward detecting Earth mass planets. These programs require patience, years of observations, careful calibration, but they're delivering results, finding planets no other method can detect. Direct imaging surveys use coronagraphs and adaptive optics to photograph planets around nearby young stars. These surveys are sparse. Imaging campaigns might target hundreds of stars and find a few planets. But each image is precious, direct light from another world, and future instruments will improve. Larger telescopes, better coronagraphs, more sensitive detectors. The direct imaging yield will increase, enabling spectroscopy, characterization, understanding. International collaboration makes this possible. Exoplanet science is global. Telescopes in Chile, Hawaii, Canary Islands, Australia. Space missions from NASA, ESA, others. Researchers from every continent. Data shared openly. Papers co-authored by scientists from dozens of countries. This collaborative spirit accelerates progress. No single nation could build all the necessary infrastructure, but together, humanity can, and we are. Building telescopes, launching missions, training scientists, analyzing data, discovering worlds. The exoplanet revolution is a human achievement, not just American or European or any single country. It's humanity's achievement, and that's powerful. It shows what we can do when we work together toward common goals. The data archives are public treasures. Every observation from Kepler and TESS is publicly available. Anyone can download it, analyze it, search for planets. Amateurs have found planets this way, by examining data professional astronomers missed or hadn't gotten to yet. Citizen science projects like Planet Hunters engage thousands of volunteers. They look through light curves by eye, identifying candidate transits, flagging them for professional follow-up. This democratizes discovery, makes exoplanet science accessible, and it works. Volunteers have found planets, published papers, contributed to the field. This openness is unusual in some sciences, but standard in astronomy. And it enriches the field, brings diverse perspectives, finds things automated algorithms miss, engages the public, makes people feel invested in the discoveries. Education benefits enormously. Exoplanets captivate students, make astronomy relevant, tangible. These are real worlds we're discovering, not abstract concepts. Students can analyze real data, plot light curves, calculate planet properties, experience the thrill of discovery using the same data professionals use. This transforms education, makes it active, engaging, connected to actual research, and it inspires. Some students become astronomers. Others appreciate science differently. Either way, value is created. Understanding spreads. The next generation grows up knowing planets are common, knowing we're searching for life, knowing the universe is full of worlds. This perspective shapes how they think about humanity's place, about the future, about our responsibilities. It's education in the deepest sense, not just facts but perspective, not just knowledge but wisdom. The philosophical implications ripple outward. If planets are common, if potentially habitable worlds number in the billions, if life might exist elsewhere, this changes existential questions. Are we special? Not in having planets, maybe not in having life either. Does that diminish us or enrich our understanding? I think enriched, because it means the universe is full of stories, full of worlds with their own histories, their own processes, maybe their own observers wondering what's out there. We're part of something larger, participants in cosmic patterns, not isolated exceptions, but examples of what the universe does. It makes worlds, it creates conditions, and, at least sometimes, it makes life. Consciousness, observation, we exist, and probably we're not alone in existing. That's profound, that's meaningful, and it's what the exoplanet discoveries point toward. Not proof yet, but strong suggestions. The ingredients are there. The opportunities are abundant. The stage is set. Whether life uses those opportunities remains to be seen. But we're looking, we're searching, and maybe within our lifetimes, we'll know. We're living through a golden age of exoplanet discovery, a time when the technology and the will coincide, when we're capable of detecting worlds around other stars, and we're doing it. In 50 years, when the catalogue numbers in the tens of thousands or hundreds of thousands, people will look back at this era as the beginning, the time when we first learned that planets are everywhere, the time when we started characterizing them in detail, the time when we began searching for life beyond Earth. You're witnessing this. You're part of it. And whether you realize it or not, you're living through one of the great revolutions in human understanding. A shift from wondering about other worlds to knowing they exist. From imagining what's out there to seeing it. From being alone in our knowledge of planets to cataloging thousands. This is history, and it's happening now. The exoplanet revolution has transformed our view of the universe, made it less empty, more full of worlds, more full of possibilities. And as we continue exploring, as we find more planets, as we characterize them in increasing detail, we'll learn even more about how common Earth-like worlds are, about how often life arises, about whether intelligence is rare or common, about what kinds of civilizations might exist, about our place in a cosmos filled with worlds. This is the journey we're on, the journey of understanding, and the discoveries are just beginning. Thank you for joining me in exploring how many worlds we've found beyond our solar system, and remember that each of those 5,000 confirmed exoplanets represents a real place, a real world orbiting a real star. And the universe is full of such worlds, more than we can ever count. Each one an opportunity for discovery. Each one a reminder that the cosmos is vast and wonderful and filled with possibilities we're only beginning to understand.